Think of a capacitor as an electrical pressure vessel. Its entire job is to trap and hold electrical charge. To understand how it holds that pressure, we have to look at its simplest architecture, the parallel plate capacitor in a vacuum. It consists of two plain metal plates, defined by their surface area, A, and separated by a specific distance, D. This equation shows the baseline capacitance for that vacuum setup. At this stage, electrical storage capacity is strictly a matter of geometry. You get more capacity by increasing the area of the plates or decreasing the distance between them. But there is a physical limit to this design. As you push more charge onto the plates, the voltage rises. Eventually, the electric field becomes so intense that the vacuum itself breaks down and the charge violently sparks across the gap. You might assume that putting a physical object in the middle of that gap would disrupt the system. But if you slide a solid insulator, known as a dielectric, between the plates, the electric field actually softens. This obstacle multiplies the amount of charge the plates can safely hold. Why does placing a physical roadblock directly into an electric field make the system vastly more powerful, rather than breaking it? To find out, we have to zoom past the large metal plates and look at the microscopic structure of the dielectric slab itself. Unlike a metal conductor, which has free-flowing electrons roaming around, a dielectric is an insulator. Its charges are strictly bound to their parent molecules and cannot flow freely across the material. When the massive electric field from the metal plates hits them, these bound molecules react. The positive and negative charges within the molecules are pulled in opposite directions. The molecules physically stretch or rotate to align with the field lines, forming dipoles. A dipole is a molecule with a distinct positive and negative end. This happens everywhere at once. Across the slab, billions of previously random molecules suddenly lock into uniform alignment. Because they are perfectly stacked in a grid, the positive end of one molecule sits directly next to the negative end of its neighbor. Throughout the interior of the material, these charges effectively cancel each other out. The only places they don't cancel are at the far edges. This leaves an unneutralized layer of charge on each face of the dielectric. We call these specific boundary layers induced surface charge densities, represented mathematically as positive sigma p and negative sigma p. Pointing opposite, these vectors subtract. The dielectric's field cancels a portion of the original, leaving a significantly weaker net electric field. Electric field strength and voltage are directly linked. When the net field drops, the potential difference, or voltage, across the plates drops right along with it. The physical amount of charge sitting on the outer metal plates has not decreased at all. The only thing that changed is that the voltage hurdle holding that charge in place has been lowered. By lowering the voltage while maintaining the exact same amount of stored charge, the capacitor is now able to accept even more electrical energy. We can see how this microscopic battle affects the final capacitance by looking at the core equation for capacitance, charge divided by voltage. When the dielectric steps in and shrinks that voltage number, the denominator in our fraction gets smaller. Dividing the exact same charge by a smaller voltage forces the overall capacitance to climb. Looking at this modified formula, the scale of that climb is dictated entirely by a property called the dielectric constant, or K. This is a unique multiplier for every material that dictates exactly how strongly it polarizes and drops the voltage. When we multiply the vacuum baseline by this constant K, we get the permittivity of the medium, a single value representing how well that specific material tolerates an electric field. That brings us to our final equation, C equals K times C0. The new capacity is simply the original vacuum capacitance multiplied by the dielectric constant. Adding an insulator aligns billions of molecules, creates an opposing internal field, and drops the overall voltage. This atomic tug-of-war is what ultimately multiplies the system's storage power by the exact factor of K.